Record. There we go. We are on Unit 4 today. For those of you who are watching this recording in the future, I might not get through the entirety of today's lecture. I might have to record it at a later time. So if it comes in two parts, that's why. So we are starting Unit 4, which is the last unit of our Calculus 1. I had mentioned before how the breakdown works. I don't know if it was during the review or if it was during class. I think it was during class last week. Basically, Unit 1 or Exam 1 covers Unit 1. Exam 2 covers Unit 2. Exam 3 covers Unit 3. And then the final exam is going to cover all of these, and it's half the exam is going to be Units 1 through 3, and then the other half of the exam will be Unit 4. So there won't be an exam that comes that's just Unit 4, but there will be half of the exam material for the final exam will be Unit 4 material. So just so you know kind of what we're looking at. So half the final exam, since it is comprehensive, will be from Units 1 through 3. Half of it will be from Unit 4. So this stuff will still be tested on, even though it doesn't have its own special exam. It's really important if you're going on to Calculus 2 that you pay special attention now. I know it's really easy to tune out, especially since lockdown makes it really hard for anyone to pay attention to anything. I get it. I totally do. I know we're getting closer to the holidays and the brain kind of wants to check out anyway. And then you put the COVID thing on top of it and the quarantining, and it makes it really hard to just kind of stay in tune. But the stuff you're going to learn right now, your Calc 2 teacher is going to expect you to know it coming in. Some teachers, they don't put enough emphasis on this material at the end, and it becomes a problem because you get into Calculus 2 and your teacher will expect you to know it hands down. So if you can just muster up that energy to, get through this last unit and keep this material in your head and take it seriously, it'll benefit you when you get to Calculus 2. So that's that. All right, let's start talking about the last part of calculus, which is integrals. Sorry, my dog just barked. I'm going to expect my husband's going to take him out. So we started talking about antiderivatives. And when we talked about just derivatives, we talked about derivatives being like that there was a connection between derivatives and the slope of the tangent line, right? There was a connection between derivatives and the slope of the tangent line. Then we started talking about antiderivatives. And you might wonder, like, okay, graphically, what is an antiderivative doing for us? And the answer is graphically, the antiderivative relates to an idea called integrals, which relates to the idea of area. So here's the motivation for talking about integrals / antiderivatives. We're going to talk about something that seems completely different than anything we've talked about. We're going to talk about area. So if you have a graph, let's say you have this graph right here. This is y equals x. And you wanted to find the region under the curve. You're going to hear these words a lot, region under the curve. So it's that first, if you're looking at this like first quadrant, the area underneath this curve between two different numbers, we could find this area, right? Like if I look at this right here is a triangle. I could find this area. No big deal, right? This is the line y equals x. This is 10. This is 10. I know the area of a triangle. It is 1/2 base times height, which is 1/2 10 times 10. That's going to be 50. Cool, done. I can find that area. All right, no big deal. We are on a roll. And even, hey, this guy over here, this is a half circle. I could find this area. This is the equation of this curve right here. And I could find this, right? This right here, we know the area of a circle is pi r squared. So the area of a half circle is 1/2 pi r squared. And it looks like we have a radius here, right? So it's this, the diameter is 12, so the radius here is 6. So the area of this would be 1/2 pi times 6 squared, which is going to come out to be, let's see, 18 pi. So we can figure that out. That we can find out those areas. That's excellent. However, if you look at this picture here and you say, what is this area? What is this shaded area in here? I wouldn't expect you to give me a good answer. But I would expect you to have ideas for how to start figuring this out. So looking at this, all right, let's just go back to like kindergarten type math or like middle school type math. Looking at this, not thinking about calculus, if I asked you to find this area here, you'd probably come up with a few different ideas. You would probably start being like, okay, well, we can kind of like count the squares, right? Like you could like count the squares and be like, okay, well, there's this many squares here. There's, this many squares here. You have like a partial square, another partial square. Maybe those make one square. Or maybe what you would do is you'd start kind of like drawing like little rectangles in here. Like I could look at this rectangle. Let's see. I think this is 0.1, 0.2, 0.3, 0.4, 5.6, 0.7, 0.8, 0.9, 1. Let's see. So this first rectangle would have an area of it's a 0.1 wide and it's 1 tall. So this first rectangle would have an area of 0.1 times 1, which is 0.1. And then maybe you're just going to kind of like say, okay, we'll look at this rectangle too. We could add this one to it. And this guy would have the same width, the same height. And then maybe with this one, you're like, oh, well, maybe we're like here-ish. This is like, the height on this one is like, let's see, the width is still 0.1. The height on this one would be like, I don't know, 1.05. Right? So you're going to get 0.105. And you could start adding those together, right? I could like make a bunch of rectangles here, and I'm not going to do that. But I could make a bunch of rectangles here, right? And I could estimate it, right? I could estimate by making a bunch of rectangles. I would just continue kind of making rectangles this entire way and adding up those rectangles. I could totally do that. That would be fine. So we're going to use that same idea that we'd kind of use in like maybe kindergarten or middle school or, in our earlier math classes where we would add up rectangles to estimate an area. That's where this whole thing starts, is adding up a bunch of rectangles to estimate area. There's actually rules that go beyond rectangles. There's making trapezoids. There's a lot of fun stuff. But there's a bunch of different ways you can make rectangles. There's a bunch of different ways you can make rectangles. And that's what this section is going to be talking about, is how can we decide on what rectangles we're going to make to estimate the area under a curve, to estimate this shaded area. Down below are some examples of ways you could have done this. So like what I was doing here, you'll notice that I was making my rectangles a little different. I was like going up and then over. But this one, the rectangles are being drawn from where the right endpoint is. Here, they made the rectangles a little bigger. So they made them 0.25 wide instead of 0.1 wide. But notice that the smaller in width that your rectangles are, the more accurate your area is going to be. Like if we add up all these rectangles, it'll be closer to the actual area than if we add up these rectangles here. All right. So for this guy here, we have a graph. It's given twice. And we're going to approximate this area beneath the graph using 3 rectangles and 6 rectangles, and we're going to go from -1 to 2. So let me kind of shade in what this is looking like. -1 to 2. We're looking at this area right in here. We're trying to approximate that area. Now, in calculus, we're going to oftentimes go with these right-hand endpoints, where not like the ones I drew up here, but where the rectangle the height of the rectangle is defined by where the endpoint is on the right-hand side. So just going to mention that. So we're going to draw rectangles here, and then here it says, hey, we should use 3 rectangles. We should use 3 rectangles to estimate this. So how do we do it? If we only can use 3 rectangles, they should be equal in width. They should be equal in width, right? The total width right here, if you do 2 minus -1, that'll tell you the total width here. So the total width is 3. So if the total width is 3 and we want to make 3 rectangles, how wide should each rectangle be? If we want to make 3 rectangles and it's 3 units wide, how wide should each of those rectangles be? One unit, yeah. They should be 1 unit wide. So, right, we're going to have those rectangles be 1 unit wide. And we're going to use what we call right-hand endpoints. So I'm going to go to the right hand of this first rectangle and draw a line over. And that will be my first rectangle. My second rectangle will be right here. And my third rectangle will be right here. Now, we really should be plugging in to this equation to find out the y values, but it does look like the y values are pretty, what's this? Let's see, go down. It does look like those y values are pretty easy to find here. It looks like they hit the graph pretty nicely. So we're just going to go ahead and maybe I'll call him R1, R2, R3 for rectangle. We're going to find these areas. So we know that the width on each of these is 1. Right? The width and the area of a triangle is length times width. So the length on this rectangle, well, it looks like it goes up till 9. So the area of this first rectangle, 1 times 9, is 9. For the second rectangle, same thing. Width is 1, and then its height, or its length, is 4. For this next rectangle, its width is 1, and then its height, right here, is 3. If we add up all of those rectangles, we're going to get 16. So the approximate area of that region would be like 16 square units. Now, we're not going to end up putting units on these ones for reasons. It just doesn't really end up having units in the end. But 16 square units would be the good approximation using 3 rectangles. Now, That's going to be a little bit less than what the actual area is, but it would be an approximation. We can do that same process with 6 rectangles. From, again, -1 up to 2. With 6 rectangles, how wide should each of those units be? If you had 6 rectangles. Once again, this is the same, let's see here. This is the same distance. This is 3. Well, I hear 1/2, right? So if you have 6 rectangles over 3 units, each rectangle should be 3 units divided by 6, 1/2 units wide. So when we do the math on this one, we know we're going to have 6 rectangles. We know we're going to have 6 rectangles. And we know the width on each of these is going to be, I'm going to just write it as 0.5. The last part of this then is finding the height of each of these. Right? We have, now some of these aren't going to perfectly hit on the grid. So for those of them that don't perfectly hit the grid, what we need to do is figure out the height. The way that we can figure out the height is by plugging the x value for each of these into the original function. Right? Here it hit the grid nicely, but not all of these hit the grid nicely. So for instance, to find out, let's just say this first value here. We know we're looking at this height value, which happens at the x value. Let's see, that's -1. This is -0.5. -0.5. That's the x value right here. So you plug that back into this original function up here to find out what the y value is, what the height of that rectangle is. So you're doing f of -0.5. So -0.5 cubed minus -0.5 squared minus 5 times -0.5 plus 9. Knowing how to use the store feature on your calculator here is widely useful. You'll find it helps a lot. Right, and I get 11.125. So what I want you to do, I want you to go through and find these remaining heights and fill in these things. For each of them, you're going to have to figure out what the x value is down here and then plug it into this function. And then you're going to have all these numbers here, and then you can multiply across. So 0.5 times 11.25, you'll get an area for that rectangle. And then you're going to add all those areas up. So go ahead and give that a try. I know it takes some time. I'm going to give you 5 minutes to try this out. Just see how it goes. All right. I'm going to pause it, give you a moment to try it out. All right. So let's see. Am I recording? Okay, good. So Don't worry, this isn't going to be the only, I'm trying to kind of give an abstract idea here, but I promise I'm going to break this down even more. So for each of these, I just want to talk about the x values you're plugging in first. So for this x value, we plugged in negative 0.5 to the function. For the next one, you'd be plugging in x equals 0 to the function. For the next endpoint, you're looking at 0.5. For this endpoint, you're looking at 1. For this endpoint, you'd be looking at 1.5. And for the last one, the x value would be 2. So these are the x values you're plugging into the function to get the values I'm about to give you right here. So for R2, you should be getting 9. And I think I'm just going to erase this guy here. For R3, 6.375. For R4, you get 4. From R5, you get 2.625. And from R6, you get 3. And if you do this multiplication, you'll get 5.5625 for the first rectangle, 4.5 for the second rectangle, 3.1875 for the next rectangle, 2, 1.3125, and 1.5. And you're adding up all of these numbers, adding up all the areas of these rectangles, and you should get 18.0625 as the new estimated area. Now this is kind of messy. This is kind of messy, and it feels like there's a lot of figuring it out. But I promise you that this is all algorithmic. And this is the place where it all starts. So it's important that we find nice ways to organize our work. How did this one go for? Did anyone get 18.0625? And it's okay if you didn't. I'm going to go through some more examples, and I'm going to kind of break it down more to make sure that we're all looking at the same thing. I'm going to try to make it a bit easier. I think it went fine. Okay, cool. I'm going to go ahead. I'm going to go to another, well, maybe I'll let you finish writing down these numbers because you might still be writing these down. I think I am going to, I'm kind of thinking ahead to the notation I want to use. I think I'm going to start using A's for my areas of the rectangles because I realize now that I use this R notation for something different. So I'm going to start using A's for the areas of the rectangles. Yeah. So I'm going to put in a new page here. Just a brand new page. And I'm going to go through a new example. You might just need a scratch piece of paper here. And I'm going to kind of go through a bit more. Let's see. Details. All right. So we're going to approximate the area under the curve y equals x squared plus 4 from 0 to 8 using 4 rectangles and what we call right-hand endpoints. And I want to talk about what right-hand endpoints are, what left-hand endpoints are, and I kind of mentioned it out loud, but I'm going to really kind of drive home visually what they are. And then I'm going to talk about midpoints. So the graph of y equals x squared plus 4, it kind of looks like this. Y equals x squared plus 4, where this is 4 right here. And let's see. If we're going from 0 to 8, and we're making 4 rectangles, I'm just going to put I'm going to put all the numbers in here. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to copy this. I'm going to do a little bit of computer trickery so I can fit 3 of them here. Man, the future is amazing. I know you guys don't have the luxury, unless you're doing your notes on an iPad. I know you don't have necessarily the luxury of doing that, but man, is that nice to be able to do. All right, and now I'm going to talk about right-hand endpoints, left-hand endpoints, and midpoints. I'm going to try to break this idea down. So, with right-hand endpoints, this is the one we're going to be using most frequently. It means that the rectangles that you're drawing are going to have their height defined by the right side of the rectangle. Now, if there are 4 rectangles and we're going from 0 to 8, it would make sense that the width of each rectangle would need to be 2, right? That makes sense, right? The width of each rectangle would need to be 2. And with the right-hand endpoints, you go up on the right side and then over. Up on the right side, make a straight line if I can, and then over. Over. Up on the right side and over. Up on the right side and over. And these right here are the rectangles that I look at with right-hand endpoints. The height is coming from the right side of the rectangle. With left-hand endpoints, another way we could draw these rectangles would be if the height, so somebody, asked a question. So the question was, so do we pass the line before we go over always? How do I know when to go over? So with the right-hand endpoints, I know that my rectangles are 2 units wide. So I go to the end, I go to the right side of the rectangle, and that's when I'm going over. So with the right-hand endpoints, and this is with the right-hand endpoints, you're going to the right side and then over. Right side of the rectangle, then over. Right side of the rectangle, over. Right side of the rectangle, over. All right, good, excellent, excellent. If there's more questions, feel free to shoot them out. So for the left-hand endpoints, you still know that your rectangles, you know they're going to be 2 units wide still. But with the left-hand rectangles, right, you're going from the left side of the rectangle over. So the first rectangle is there. For the second rectangle, this is the left side, over. This one, left side, over. Left side, over. And this would be left-hand endpoints. So that height is coming from the left side we'll just write it right there, from the left side of the rectangle. Finally, we have something called midpoints. And sometimes in a regular semester, I would go over midpoints and we'd actually, do some of these with midpoints. I'm probably not going to do any with actual midpoints, or even maybe, I don't even know if I'm going to do left-hand endpoints. I just want you to know what they are. I'm going to describe what midpoints are, but because the process it takes time and there's more important things for you to know, I'm not going to ask you to do, I don't think, any with left or midpoints. I just want you to understand what these are. So for midpoints, once again, we do have these rectangles that are 2 units wide, and I'm just going to go ahead and kind of draw this. With midpoints, you take the middle of each rectangle and you find that height, and that's a really crooked line. And you use that midpoint of the rectangle to determine the height. So this is the middle of the rectangle. Maybe I should make those blue. So you have 4 rectangles, but they're defined by the middle of the rectangle. The height comes from the middle of the rectangle. And there are other ways of doing this. Like I said, there's a method called trapezoid where you end up making trapezoids. So if you can imagine, you could also, and I will erase over this, you could also take this point and then make a trapezoid instead. You could, this point and this point, make a trapezoid. And the trapezoids are going to get you closer to that area. There's also something called Simpson's rule, which I really haven't used, and I haven't used it in so long that I've honestly forgotten how Simpson's rule even looks. There's a bunch of different ways to do rectangles or just shapes in general, or approximations, to make them as close as possible to the actual area. But you get the idea, right? The idea is there. You're making shapes and you're guessing area. That's what the idea is. Like I said, we're mostly going to focus our attention on the glorious right-hand endpoints, because there's more important things to cover, although this is a very important topic. All right, and I'm going to dive deeper into the process I already asked you to do, because I want to talk about it and make sure that you really understand what's going on. So looking at this picture that we drew over here, let's see. No, I want to make you bigger. All right, so focusing our attention in on this picture here. Right. Oh, sorry, I'm on this exercise ball and it's getting a bit getting a bit obnoxious. I'm going to name each of these. I'm going to name them, like I said, I'm going to do A's now because I realize I don't want to use R's. So I have 4 different rectangles. And I want to formalize the way we talk about the width of each rectangle. In our case right here, our interval starts at 0. So this is over the interval 0 to 8. The interval starts at x equals 0, and it ends at x equals 8. The place where we start, we call that our A value, and my internet just went down on my computer. I hope it didn't go down on my iPad. My iPad's been pretty trusty. Give me a moment. Okay, I'm reconnected. We're good. My husband's yelling at me. Hold on. Sorry, my husband was yelling, your internet go out? Yeah. Make sure I keep on stopping and recording it. All right, so the place where our interval starts, we call that that value A. Right? We call it A. And the place where our interval ends, we call that value B. And the way we find the width of each rectangle and this will work for any amount of rectangles over any interval, we call the width of each rectangle delta x. It means the change in x. We call it delta x. That's the same thing as the width of each rectangle. And what you do is you take your ending value and you subtract your starting value and you put it over the number of rectangles. Right? So A comma B is the interval, and n equals number of rectangles. And if you'll notice, I'm going to go back a slide, that's exactly what I ended up doing here, or I guess more over here. 2 minus negative 1 was 3, and I had 6 rectangles. So it's b minus a over n. And I got the width of each rectangle, which we're now going to call delta x. In our particular case here, we're from 0 to 8, and we have 4 rectangles. So our delta x value is 8 minus 0 over 4, which is 2. Right, we are formalizing this idea so that we can use it in any case whatsoever. Now what we're doing to find the height in the right-hand endpoint case, to find the height of each rectangle, we're going to plug the right value into the function. And I will write that down. So for example, for our first rectangle, this is what she looks like. We know that the width is 2. That's our delta x, by the way. The width is 2. So let me just draw on here. Delta x is the width of the rectangle, and all the rectangles have the same delta x. They're all 2 wide. And then the height of this rectangle comes from plugging in this x value 2, right here, 2, into the function y equals x squared plus 4. So we're doing 2 squared plus 4, and that gives you 8. The area of our first rectangle is 2 times 8, which is 16. Right? I'm going to slowly do this for the rest of these rectangles. All right, so again, for this rectangle, it's a width of 2. Now, for the second rectangle, notice that the x value is 4 here. This x value down here is 4. So we're plugging 4 into the function. And 4 squared plus 4 gives me 20. So the area of the second rectangle is 2 times 20, which is 40. I'm going to write the rest, I'm going to write A3 and A4 down, but I want you to kind of like maybe look away from the screen real quick. Maybe I'll be silent while I write them down. Maybe I'll pause the video and be silent while I write them. Try to do A3 and A4, right? Try to do A3 and A4. Try to get this practice in. So I'm going to pause the video. I'm going to be silent, but I'm going to write them down. If you want to just follow along, you can, but try to do it yourself. So I have all those areas written down now. How are those areas looking for you guys? For areas 1, 2, 3, and 4. Got them? Good. Excellent. So then our approximate area is just adding these all up. So you're just adding A1 plus A2 plus A3 plus A4. So we have 16 plus 40 plus 80 plus 136, and we get a total of 272. All right, so this was this example. I want to do another one, but I want to show you how we can organize our work so that it looks even nicer. All right, don't have to use my organization methods, but I think that they're handy. Oops, I'm going to make a new page in here. So I'm going to do another example, and I'm going to show you how I organize my work, how I like to. And it's going to be a very similar question. All right. So we want to approximate the area under the curve y equals 4x plus 1 from x equals 2 to x equals 4 using right-hand endpoints and 4 rectangles. Sometimes it can be useful to draw yourself a picture. Like a lot of times it can be useful to draw yourself a picture. So I'm going to just draw a quick picture here. So maybe actually I'll move those numbers over a little bit. All right, so I'm drawing a picture. I know that I am going from 2 to 4. So my interval that I'm looking at is from 2 to 4. And there are 4 rectangles. So I know n is equal to 4 because I have 4 rectangles. I'm going to draw myself the quick picture of what this should look like. So I know I begin at 2, right? And I know I end at 4. And if I have 4 rectangles, you know, I know it's going to be something like this. I know I'm going to have to draw some lines in here, but it's going to be something like this, right? My delta x should be b minus a over n. Now looking at this picture, it looks like my delta x should be 0.5, so we should see if that's what we get from here. This is going to be a is 2, b is 4. So we have 4 minus 2 over 4, which is 2 over 4, which is 1/2. Well, that makes sense, right? That makes sense. My width of each of these rectangles is going to be 1/2. If I just kind of draw these in, I'm doing right-hand endpoints here, so I'm going to the right of each rectangle and drawing over. And I have 4 rectangles. The important thing to remember is that the area of each rectangle is equal to the height times delta x. Right? This is the important thing. Area is equal to the height times delta x. I'm going to make a chart. And I wish I could draw straight lines. Yeah. Excellent. So like if we're talking about the actual area, yes, absolutely. Absolutely. However, with Riemann sums, so this process we're doing, these are called Riemann sums, and the approximation is going to be either over or under in almost every case. There are some cases where it turns out to be the exact area, but with Riemann sums, because a lot of times it's not nice like this, it's like kind of curvy, there's no way for us to actually get like an exact measurement. So we use these approximations. Does that make sense? All right, no problem. All right. So then here's how my labeling is going to work. I'm going to have an x value column. I'm going to have a height column. I'm going to give it a little space here. A delta x column. And an area column. And I'm going to move it down a little bit. In the end, you end up getting the height times delta x is equal to the area, right? Just so we are clear here. But for each of these, what I'm going to do is I'm going to find the x value from the graph I have up here. Right? I'm going to look at this graph, and I know that the first rectangle has their height coming from the right end of the triangle, and that's at 2.5. So the x value we're going to use for A1 is 2.5. The x value you're using for the second rectangle is 3. For the third rectangle, I need more colors, right? Their height is coming from 3.5. That's what that x value would be. And the last rectangle, maybe I'll just do it in blue, right? The last rectangle their height comes from the left side of the rectangle, which is 4. This column I'm doing over here, this x value thing, ends up being what tells, pointer, what we use to plug into the height. So we're going to take these x values for the height, we're plugging it into the function. So these are what x value do I plug into the function to get the height? Now, the function is 4x plus 1. So when I go to find the height, I'm doing 4 times this x value plus 1. 4 times 2.5 plus 1, which will give me 11. 4 times whatever that is plus 1. I'm going to come back with the color so I can do it all in one go. So 4 times 3 plus 1, that's 13. 4 times 3.5 plus 1, that's 15. 4 times 4 plus 1, that's 17. The delta x is always the same, right? That's always the same. This delta x right here, same for everybody. The width of each rectangle is the same. And just so it's clear, because I don't think it looks very clear here, this is a multiplication. Let me zoom in. Height times delta x, so it's like width times height, is equal to the area. So you're just taking the height and the delta x, multiplying together, and getting an area. So 11 times 1/2 is going to give us 5.5. 13 times 1/2 is going to give us 6.5. 15 times 1/2 is going to give us 7.5. 17 times 1/2 is going to give us 8.5. And then we add those areas together to get an approximate area. All right, so we have 5.5 plus 6.5 plus 7.5 plus 8.5, which will give us, let's see, 11 plus 15 is 26 plus 2, 28. I hope. Now, you could even do this without drawing a picture here. Right? You can do a more rudimentary process here. Let's say I didn't know what 4x plus 1 looked like. Let's say I just don't know what 4x plus 1 looks like. And I'm trying to fill out this frickin' table here, but I don't know what 4x plus 1 looks like. That's okay. You can draw. You know that your interval starts at 2 and ends at 4, right? You start at 2, you end at 4. And you know the delta x. You know the delta x is 0.5 or 1/2. Right? You know that the delta x is 0.5. So you can just start counting by 0.5s. Right? 2 plus 0.5, right? This is 0.5 wide. Well, that would be 2.5. And then the next one should be 0.5 wide. Okay, well, 2.5 plus 0.5 would be 3. All right, well, this one has to be 0.5 wide. 3 plus 0.5 is 3.5. And obviously those didn't turn out very evenly split up, but there we go. And then if you're doing right endpoints, right? So you know that each of these are a chunk, right? One chunk, one rectangle, one rectangle, one rectangle, one rectangle. You're taking the right side of each of those. So this guy would be the x value for A1. It's the right one. This one would be the one for A2. This would be the one for A3. This would be the one for A4 because you're taking the right side of each of those rectangles. So you could do this even if you didn't know what the picture of the graph looked like, because in the end, all you really needed to fill out this chart was the x values and then whatever the function was. We know it was 4x plus 1. We didn't need to know the shape of 4x plus 1, though. Can I answer any questions there? So before we get on to like some pretty, I guess, nasty-ish notation, I want to go back and I want to try doing another one. I kind of want to go back to these examples here, and I want to choose a different interval and have you guys, maybe not that example, I'll just do a different one. I'm going to give you one to try so that you can try it. I want you to practice this process. Let me just make sure I get a number that's going to be mostly okay. There we go. Wait, 6 rectangles. I'd like you to try using that chart, doing the same kind of chart as last time. So you're approximating the area under the curve y equals 2x squared plus 3 from x equals -2 to 7 using 6 rectangles and right-hand endpoints. Go ahead and do that. I'm going to give you, let's say, I'm going to give at least 6 minutes to try this one out. Go ahead and start on that. All right, so my timer went off. It might not have been enough time. How is it going so far? Let's get an update on how people are doing right now. Not bad? Okay. I'll take not bad on A4. Okay. Maybe I'll give like another 2 or so minutes so you guys can finish them. So I'll go ahead and put another 2 minutes on just to give you guys time to finish. All right, so I'm going to go ahead. That was the 2-minute mark. I'm going to go ahead and start working on the answer to this problem. So to begin with, this is where we're beginning. This is where we're ending. So those are our A and B values. And when it says 6 rectangles, that means n is equal to 6. So if we're finding delta x, which is b minus a over n, we have b is 7 minus negative 2 over n is 6. So that's 9 over 6, which is 1.5, because it reduces to, or 3 over 2, whatever you want to put it. 3 over 2, 1.5, same thing. And I can put that in here for all of these, for all the delta x's. For these x values, however you want to set it up, if you want to make yourself like a little chart, if you're making a little chart for this to figure out like what the x value should be, you know, you're beginning at negative 2, and then it should be 1.5 long. So negative 2 plus 1.5 is negative 0.5. That'll be your first x value. And then really, because this is our first rectangle, right-hand endpoint, then really you can just take this number and keep adding 1.5 to it. Negative 0.5 plus 1.5, so plus your delta x, is going to be 1. 1 plus 1.5 is 2.5. 2.5 plus 1.5 is 4. 4 plus 1.5 is 5.5. And 5.5 plus 1.5 is 6. That's how I do it in my head. These heights, once again, they come from plugging in to your function up here. I'm not going to write down doing that, but I'm taking this x value and plugging it in here. So the values I got 3.5, 5, 15.5, 35, 63.5, and 75. Okay. Yeah. Yeah. Definitely. Sorry, I was looking at your comment. I was like, wait, when did that comment come? Yes, it is 7, which means this number's off down here because my head did not work right there. 7 store x. So this number down here should be 296 point, or no, that's not right. Give me a moment. 101, right? Is that what we're getting down here? Yes. So that one should be 7. Good catch. And then for the areas, you're multiplying height by delta x. So 3.5 times 1.5 should give you 5.25. This one should be 7.5, 23.25, 52.5, 95.25, and this one should be 151.5. Adding all those numbers up, now I have to redo my number because I plugged in the wrong one. Hold on, minus 112.5 plus 151.5. This should be 335.25 as an area. How did that one go for everybody? Favorite section. Love it. You may kind of take those words back when I get to the next page. But I'm going to try to limit some of the stuff from the rest of the section that gets a little bit, I think, more complicated than we need to be. At this point in the semester, we have, a little time left. We are in week 12. There's really like 15 weeks of the semester. So we have week 12, 13, 14, 15, and we have like 4 more weeks and then finals week. My goal is to give you the most important information. So some of the stuff we're about to get into in this next page, rest of this particular section, not unit, but this section, is very notation-y. And I have to give you some of it, but I'm going to try to limit what I give you so that it's not entirely overwhelming and that you're not worrying about the wrong stuff. Riemann sums are important so you understand what's going on. The notation we're about to get into is something that will come up again in 182 in calculus 2 in a bigger context. So I have to give it to you in at least a little bit. But I'm going to try to keep it as limited as possible. So without further ado, let's get to summation notation. All right. I know this looks messy. All right. This looks really messy. I'm going to try to make this as nice as possible, though. So summation notation talks about sums. Summations are sums. And I want to talk about this little notation-y thing up here. Essentially, what summations tell you to do is they tell you to add up a bunch of different numbers, and each number kind of has a formula that goes with it. There's some names to this stuff up here. First of all, this guy right here is a capital sigma. It is a Greek letter, sigma, which is kind of like the English letter S for sum. There's a lot of Greek letters in math, you know that at this point. But this is the Greek letter sigma, and it stands for sum. So we call this sigma notation. Sometimes we call it summation notation, but it's sigma notation. Here's what's going on here. It's going to tell you, this little I down here, that stands for index. It's kind of like your variable. It's kind of a variable. This M right here, we call it the lower bound. It's where we start. And this N up here, we call that our upper bound, and that's where we end. So essentially, we're going to have some formula involving, some cases i's, it can be different depending on what your index is. We're going to have some formula in here that has whatever your index is, and we're going to start plugging values in, starting with M, going to N. That sounds a little confusing, but we're going to get into it and it's going to be okay. So here, our index is I and it starts at 1, and it's telling us we're going to add up the sum from 1 to 10 of I. So just plugging in 1, and then we plug in 1, then we make I go up by 1. All right, so we start at I equals 1. If you plug in 1, you get 1. This is I equal to 1. Now that we've done I equal to 1, we do a plus sign, and then we make I become 2, and we're going to go all the way to 10. So if I is 2, we'd have 2. This is I equal to 2. Then I becomes 3, so plus 3. That's if I is equal to 3. And this goes on, right? I'll write it out, but I is equal to 4. I is equal to 5. I is equal to 6. I is equal to 7. I is equal to 8. I is equal to 9. I is equal to 10. We stop when I is equal to 10 because that's our upper bound. And then you just add up those numbers. You add up 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And hopefully my own notes are correct, and this is 55. So that's kind of like a really basic example of it. And it gets kind of weird, but I'll show you what this looks like. You're starting with k equals 0, you're going to 4, and this is your formula now. So essentially you're going to have a few things here. You're going to start with k equals 0, and then you're going to have one where k equals 1, one where k equals 2, one where k equals 3, one where k equals 4. And you're going to be adding up all of these. So for k equals 0, you're plugging 0 into this formula. So when k is 0, that's your lower bound. You always start at your lower bound. Plugging in 0 here, right? 0 over 0 squared plus 1. Plugging in 1. 1 over 1 squared plus 1. Now k is equal to 2. 2 over 2 squared plus 1. K is equal to 3. 3 over 3 squared plus 1. K is equal to 4. 4 over 4 squared plus 1. Just plugging in, you let k equals 0 to begin with, you start down here, and then you plug in that number to the function. And once you've done it, you do a plus sign because you're summing these. And then you go to the next number. You just go up by 1 each time. You're always going up by 1 each time. You don't have to worry about it going up by a different number. It'll always go up by 1 each time. So looking here, you're going to end up with 0. I'll just tell you it'll become 1/2, 2/5, 3/10, and 4/17. Which, if you add those in a calculator, because nobody's going to do that by hand, you get 122 over 85. Sometimes these can be a little bit tricky. So for here, look, we're starting at 3. So our index here was k. It can be k. It can be, oftentimes they're I, J, or k. Those are the typical indices. But here we have j, and we're starting at 3. So it all depends on what your lower bound is. So here I is equal to 1, so we started with 1. Here k is equal to 0, so we started with 0. Here, j is equal to 3, so we're going to start with 3. Now, this is kind of an interesting one, right? So we're starting with 3, then we're going to go to 4, 5, 6, and we're going to go to 10, 7, 8, 9, 10. And we're going to add up all of these by plugging in j. But if you'll notice, there's something interesting here, because this guy doesn't have a j in it, right? These had k, the first one had an I in it, but this one doesn't have a j at all. So if you plug in j equals 3 to this, it's still just 5, right? There's nothing to plug into. It doesn't matter that j is 3, 5 is 5. And it's going to be that way with all of these. It doesn't matter that j is 4, because it's just 5. So all of these are going to be 5 because there's nowhere to plug j into. It doesn't change each time. Something to note here. You might think to yourself, oh, that means we're adding up j, 10 minus 3, well, that's 7. Oh, there must be 7 5s here. But there's not. There's actually, if you look, there's 8 5s. So you have to be careful, because this 10 minus 3 thing, even though that feels like what you should do, you have to be careful. There's actually going to be one more than you think there should be. So like from 0 to 4, that's actually 5 different ones. So a few things Here, caution, there's no j's in the summation. So that's why the 5 didn't change. And then the other thing is that we're adding up 8 5s, not 7, even though that's what it looks like it should be. There's some notes down here for particularly tricky cases, but I'm not going to get super into that right now. I just kind of want you to get this vague idea of summation notation. Can I answer any questions about these few examples right here? So I want to maybe give you 1 or 2 to try. Maybe I'll give you 2. So we'll go from I equals 2 to 5 of I squared. And then I also want you to do the sum from I equals 0 to 4 of 2I minus 3. Right? I want you to do both those summations. Try them out real quick. I'm going to give you, let's say 7 minutes. I'll give you 7 minutes just because you're kind of learning this. All right. So let's go over these guys. I'm just going to move this guy over or down. We'll move him down. So for the first one, I'm just going to start with showing where my indexes are going to be. So I'm going to start with 2, and I know I'm going to 5. So I have 2, 3, 4, and 5. And I know that I'm adding those all up. So the first one, 2 squared, will go here. Then I equals 3, so this will be 3 squared. I equals 4 would be 4 squared. And I equals 5 would be 5 squared. So we have 4 plus 9 plus 16 plus 25. It's going to be, what, 54? Yes. So you should be getting 54 for this first one. Any questions on that one right there, on the first one? Okay. For the next one, we're starting with I equals 0, and we're going to 4. So we know we're going to have I equals 0, I equals 1, I equals 2, I equals 3, and I equals 4. And we're going to be adding these up. Now, since there's kind of like 2 parts to each of these, I'm just going to go ahead and put parentheses in here so we know that each part is separate. So plugging in now, 2 times 0 minus 3. That's for I equals 0. For I equals 1, 2 times 1 minus 3. For I equals 2, 2 times 2 minus 3. 2 times 3 minus 3. 2 times 4 minus 3. So for that I equals 0 one, you're going to get negative 3. 2 minus 3, that's negative 1. 4 minus 3 is 1. 6 minus 3 is 3. 8 minus 3 is 5. So adding those all up, we should get 5. How did parts A and B go? Pretty good. I will take a pretty good. A great, a good, I'll take all of those. I'll take every single one of those. This is the basics of summation notation. Summation notation gets more complicated. And I'm going, like I said, I want to leave, you're going to get more complicated in Calc 2. I need you to know the basics, and I don't think I'm going to make you go as far as I would maybe make us go in a regular Calc semester. I just need, I want to go through the important stuff and kind of leave it there. This is not all of the important stuff, but it is the beginning of the important stuff. Don't worry about these. These are fun examples if you really want to try them. Don't worry about these. I do want to talk about some stuff going on down here. So, for summation properties, if you have a constant out front of a summation, if you have a constant out like right here, you can pull it out front of the summation. That's what this property says. So example, if you had the summation from like I equals 1 to 7 of, let's say, 2x squared, no, not 2x squared, 2I squared, you could take this 2 and put them out front. This is what this says. So you could make this into 2 summation from I equals 1 to 7 of I squared. So you could take that 2 out front. Someone said it reminds me of factorials. Yeah, it's a close idea. Like factorials, you're multiplying things together. Summations, you're going to be adding things together. And it relates really, really nicely, if we go back, it relates really nicely to this idea, right? Because what we ended up having here was like a bunch of stuff being added together, and there were formulas to getting all of these things. So this is how they're related. Right? Down here, this says if you have two things being added or subtracted, that you could split them into separate notations. So I had 2I minus 3 here. So if I had 2I minus 3, and what did mine go from? 0 to 4. This says I could make it the sum of 2I from I equals 0 to 4 minus the sum of 3 from I equals 0 to 4. So I could split it into two different summations. I'm going to go a little bit over with my time just because I want to get through this, and I'm probably going to post another video. We won't be doing class on Wednesday, but I'll probably post a video to at least kind of finish up this section so we don't get too behind in the material. But I'm going to probably take another 10 minutes. If you have to go, that's totally fine. But I think I'm going to take another 10 minutes just to kind of get a little bit further. Here we have some rules. So these are rules that can be used just kind of in general. So you don't need to memorize these rules. Obviously, everything is open notes here. And just even in a regular calc classroom, you probably wouldn't be asked to memorize these rules. So depending at, like, as long as your summation starts with 1, you can use these rules to figure out what the sum would be. So remember when we did the sum from 1 to 10, and we said it was 55 of i's. So we did I equals 1 to 10 of I. This rule says whatever this number is up here, you can replace it in this formula. So in our case, that number was 10. So this should come out to be 10 times 10 plus 1 over 2. So 10 times 11 is 110 divided by 2. That's 55. That was the same answer we got without any adding. So these are different formulas that get used for different summations. If you have a constant and it goes from 1 to n, you could just do n times the constant. I'm not going to prove to you how these work, all right? This part is part where you're just going to have to accept it unless you want to go look up proofs for yourself. There are definitely proofs out there. You can definitely find them. Whether or not they're going to be fun, that will be up to you. You don't need to know how these work. You just need to know that they do. We did this one by hand, and we knew it came out to 55, and here's using the formula. That's not a definite proof that it works, but it's a little bit of convincing, right? Did I do any ones that started with 1? No, I don't think we did any ones. No, that one started with 1 and 0. So these ones only work with 1, and I'm not going to talk about reindexing. So we're not going to talk about that. So I want to use these formulas, and I'm going to do this page right here, and that's where I'm going to end it. Once again, if you have to leave, that's no big deal. I just want to do this page here. So all of these indexes start at 1, just so you know, for these examples. And now I'm going to split these up using these rules. So the first rule says, hey, go ahead and just, this will be from I equals 1 to 9 of 2i cubed, and then we'll split it up. I equals 1 to 9 of 7. We have a rule that says we can take this 2 and put it out front. And it is important each time that you don't get lazy and do this. All right, I know it's tempting. I know you want to just leave off the bounds, but I'm going to be picky about it. It takes 2 seconds. The exams are open note. You have a lot of time to do them. Put the darn notation in. The upper bounds, the lower bounds. Now, maybe if I take a screen. Okay, I hope that didn't mess up that segment. That might have messed up that segment because I took a screenshot. I hope it didn't mess up that segment. I just wanted to take a screenshot so I could have the formulas on this page for us. So for this guy here, we're using the I cubed. So this thing right here, the I cubed, we're using this formula right here. In this case, our n is 9. So we have 2 times, and now I'm plugging 9 in for this formula here, because this is I cubed. So I have 9 times 9 plus 1 over 2 quantity squared, minus, for this guy, this is a constant. So the constants, it says that we're doing whatever the constant is times our upper bound, right? So our constant is 7, and our upper bound is 9. So this is 9 times 7, using that formula right up here. So using my handy dandy calculator here, let's see, that'll be 90 over 245 squared times 2. I get 4050 minus 63 for a total of 3987. And I promise this comes in handy. All right, so moving down to this next one, same idea. We're going to split it up. So we have the sum from k equals 1 to n. Now, there's just an n there, so we don't have anything we're going to be able to plug in the end except for n, of k squared over 3 minus the sum from k equals 1 to n of 2. This 1/3, because it's like secretly a 1/3, that can be pulled out front. So we can pull out a 1/3 from k equals 1 to n and just have a k squared left, minus the sum from k equals 1 to n of 2. This is where your homework is going to start looking really fancy. It's where you're going to show it to your friends and they're going to be like, wow, so smart. Wow, super cool. And everyone will be impressed because sigma notation just looks really impressive. I promise. All right, k squared, that's this guy here. And notice we're plugging in n, and in these ones, they already have n plugged in. So really, this guy right here is exactly what we're going to replace this guy with. Because the upper bound is n, and k squared and I squared, kind of the same idea, right? So we have 1/3 times n times n plus 1 times 2n plus 1 all over 6. Minus, now this is a constant, right? The constant here is 2. And we're going to n, so this is n times 2. So if we want to just kind of barely simplify it, n times n plus 1 times 2n plus 1 over 18 minus 2n. I'm not going to simplify it more than that. There's no answer here. Our answer is going to have n's in it because our upper bound had n's in it. Let's make this one, I'm going to take this n away and make him a 20. I'm going to take that n away and make him a 20. And I'm going to separate this guy up. So I equals 1 to 20, 2i squared over n cubed. Actually, I guess I'm going to have to change a lot of this, huh? I guess don't make it 20 because there's n's in here. That's fine. We'll leave the n's alone. We'll leave the n's alone. Leave the n's alone. Now, the only variable in each of these is the I. So the n's are actually a constant. The n's are just a number. So I can bring those out front. The 1 over n cubed, actually, not even just the 1. I can bring this 2 over n cubed out front. So 2 over n cubed, I equals 1 to n of I squared. Here I can bring the 1 over n out from I equals 1 to n of I. And then I'm just making replacements. So for this guy here, it's actually just a direct replacement. The I squared one, like it's literally just this. So you have 2 over n cubed times n plus 1 times 2n plus 1 over 6 plus 1 over n, and then just the sum from I equals 1 to n of I is just this guy here. So times n plus 1 over 2. Now I know this looks really complicated, and this could be simplified. I just don't really need to take the time to simplify it in this moment. These could clearly be simplified because they have common factors, so things could get a little easier, but I'm just going to leave my answer there. But the idea of replacing is the big one, just understanding how to factor things out and replace. So now I'm deciding what I want to do for... I may or may not put out another video later this week to talk about this. Maybe I'll wait till class on Monday. I don't want to get too behind. I don't want to get too in-depth with this, but I need you to have ideas of the basics of the summation notation. So that's kind of my big thing. We need to get into this abstract notation just a tiny bit. So I will leave it here for now. I may post another video later this week. The exam will be posted hopefully tonight. Don't worry, I'll put extensions on the exam. You'll have time to do it. Um, so look out for that hopefully tonight. And thank you guys for sticking around this entire time. I appreciate you. I hope you have a fantastic, I guess, rest of the week because, again, we do not have class on Wednesday. There's no class on Wednesday. Thank you. Thanks. I hope, actually, the Tylenol did help. I'm feeling a bit better here. Thank you guys. Have a fantastic weekend.